This is our final video on rates of reaction, and it is going to be slightly larger, so I will make sure to chapter this so that you can maybe watch it in a few different sittings if you find it too long to watch all at once. This video is going to feature the calculations related to rates. Don't worry, they get easier and higher compared to National 5, but it's also going to do a comparison of average rate, which is what you know from National 5, and relative rate, which is the new way of calculating rates at higher. It's also going to look at the experimental work and setups that you might use whenever it comes to calculating or measuring the rate of reaction. So measuring the rate of reaction. In order to measure how quickly a reaction is happening, you can either look at how quickly products are being made or how quickly reactants are being used up. So you're looking at how there's a change in the amount of product or a change in the amount of reactant over time. Now, the most common ways this is done at National 5 are by measuring how much product gas has been given off by a reactant, or by measuring how much mass is lost from a reaction as time goes on. So I'm going to go over the experimental procedures for how to do this. So when it comes to collecting gas, this is the experiment that you get to do in S3 and again usually in S4 for measuring rate of reaction. And this is collecting gas via downward displacement of water. Downward displacement of water just means you've got a measuring cylinder filled with water. As the gas is produced by the reaction, the gas pushes the water down and fills up the measuring cylinder. That's all downward displacement means. So you have your reaction on the right hand side. It is completely sealed except for a tube, which then goes into a basin of water, and on that basin of water you have a filled measuring cylinder, and the gas, as it's produced, bubbles up, pushes the water down, and you can use the scale on the measuring cylinder to say how much gas has been produced. And if you were working out the average rate, you would take a measurement every minute or every 30 seconds and record it down so that over time. You would know the reaction was over when no more gas was being produced and the volume of gas in the measuring cylinder stayed the same. A slightly different approach and easier to draw approach is using a gas syringe. Now, a gas syringe just is a normal syringe, except you've got a delivery tube connected to your reaction. And as the reaction happens, the plunger of the syringe gets pushed slowly outwards so that you can measure how much gas has been produced. Again, what you do is measure how much gas has been produced every minute or every 30 seconds, and so you can see over time what's happening. Again, you could tell the reaction is over when no more bubbles of gas are being seen and the volume measured on the scale of the syringe is not changing. Now, for these two experiments, if you were to plot your results, you would get a graph that looks like this. So your time would be every minute or every 30 seconds, and your measurement would be the volume of gas. Measurement, the thing that you measure, is always on the left side on the y-axis, and your time is always on the right-hand side. So the time is always along the bottom. The rate is always quickest at the start. So at time 0, that's when your rate and your reaction is fastest. As time goes by, the rate slows down. You can see this happening because the graph starts to curve. So it starts diagonal and then it starts to curve. That curve means it's slowing down. The reason the reaction slows down is because the reactants are being used up. And finally, when the graph is flat, it means the reaction has stopped. There are no more reactants left. The other way of measuring rate of reaction is to measure mass lost. And it's usually gas that's being lost. But in this case, what you do is you just do your reaction on a mass balance, so on a scale. You make sure that the top of your reaction flask has some cotton wool in it. So the cotton wool allows the gas to escape, but it'll trap any liquid or any solid that might try and escape from the flask. So it only allows gas through. And as time goes by, the mass will drop, and you can measure that every minute, every 30 seconds by just reading the numbers on your mass balance. You'll know the reaction is over when the mass no longer changes. The graph for this just looks slightly different, but it follows the same principles. Again, time along the bottom, reaction is always quickest at the start. It slows down when it starts to curve. Again, that's because the reactants are being used up. And when the reaction is over, that's when the graph becomes flat or horizontal, because all the reactants have been used up. Now, what do you do with the information that you've collected in your table or in your graph? Well, at Nat 5, what you would do is calculate the average rate. And the average rate is the rate of reaction between two times. So, for example, it could be a few different things. Now, as the reaction keeps going, it slows down because the reactants are used up. Every minute of this reaction, we can see that the change in quantity gets smaller. And this is the rate slowing down. At the very end, when the graph is flat, your change in quantity is zero. So your rate of reaction is zero. So what we can see from average rate is that average rate is different depending on what times of your reaction you're measuring between. Now the calculation for average rate is you use the gradient. So your change in quantity divided by your change in time. So on this graph, if we're looking at the rate between 0 and 20 seconds, we go to 20 seconds, we look up on the graph, and we can see that the amount of gas produced then was 45 centimeters cubed in 20 seconds. So it's 45 divided by 20, which gives us 2.25 centimeters cubed per second. So the units of rate always have a unit of quantity. From this graph, our quantity was centimeters cubed. Then we have a forward slash and our units of time, and our units of time are second. That forward slash, whenever you're reading it out loud, is just pronounced per. So the unit's 2.25 centimeters cubed per second. There are some issues with average rate, which is why average rate is not really used so much at higher, though you do still need to know to do it because they may still ask questions on it. The problem is you need to take lots of measurements in each experiment. So you need to be really accurate with when you're taking your measurements in order to produce a very accurate graph and table of results. The other thing is that average rate is not fixed. We can see that a reaction slows down over time. So depending on what times you're using, the average rate is different. Which means it's not really easy to use an average rate of one experiment to compare it to another experiment. So if you're wanting to look at the effect of temperature, you're having to do two different experiments. Each one you're having to make lots of measurements, and depending on what times of the experiment you're comparing, the rates we know we're going to change over time, so it's not an easy thing to compare. And in fact, usually what you have to do is look at two graphs and just use the graphs to compare, which is quite time consuming. Now, if you are doing that, the rule is the steeper the graph, the faster the reaction. So in this case, I don't know why it says orange and blue, because it should be pink and purple, but the purple line is steeper than the pink line, which means that the experiment represented by the purple line is faster than the experiment represented by the pink line. So the steeper the graph, the faster the experiment. At higher, Rate is measured using relative rate, which is a much easier calculation. Now, relative rate is measured by an experimenter picking an exact endpoint for the reaction, and then just measuring how long does it take for your experiment to reach that endpoint. So you only need one measurement per experiment. It's a lot quicker to do. Now, the endpoint could be anything that you can easily measure. So a most common one would be how long it takes for a color change to happen. And you should get experience of a few different color changing reactions during this year. It could be, well, you say, how long does it take for the experiment to produce 10 centimeters cubed of gas or a litre of gas? And then for each experiment, you just say, well, this experiment took 5 seconds to produce a litre of gas. That experiment took 1 minute to produce a litre of gas. It makes it much easier to do comparisons. Or it could be using a thermometer, measure how long it takes for the reaction to increase in temperature to 50 degrees or decrease in temperature to 10 degrees. And always use that. Same endpoint, one measurement. Now, to turn that measurement into a rate, it is 1 divided by the time. Now, the time is usually in seconds or in minutes, and the units are always s to the minus 1, which is per second, or minute to the minus 1, which is per minute. So, for example, if an experiment took 10 seconds, the relative rate would just be 1 divided by 10, which is 0.1 per second. So there's no quantity in the unit, it's just a time value. This method makes it much quicker to be able to repeat experiments and to compare and measure the effects of changing things like concentration, pressure, temperature, particle size on the rate of reaction. Now, when it comes to relative rate is also affected by particle size, concentration, pressure, and temperature, but we can actually see more easily the specific ways in which different factors affect the rate. Because what you can do, once you've measured and calculated all your individual experiment relative rates, you can plot a graph of concentration against rate or temperature against rate. And we're going to look at how those graphs compare. So different conditions will have different effects on rate. So with concentration, if you were to do a few different experiments where you were measuring the rate and with each experiment you were changing the concentration, you should see, if you plotted concentration against relative rate, a straight line is what your graph should look like. And we describe that relationship as being directly proportional. And it should always go through 0, because if you've got 0 concentration, the reaction won't happen. That straight line relationship you should see for concentration, for pressure, and for particle size. It should be directly proportional. Temperature is different. Temperature, you actually see a curved graph. And this is because temperature has a much greater effect. And we call this type of curve that you see for temperature relative to rate is exponentially proportional. This means that whenever you increase the temperature by a particular amount, the rate is multiplying by a particular amount. And usually the rate doubles for every 10 degrees that you increase the temperature. So concentration directly proportional, straight line. Temperature exponentially proportional, and it's a curve. Those two terms are really good hint, hint, for you to know if you are ever asked a question about factors affecting rate of reaction. You can say that temperature affects it exponentially, concentration affects it directly. That's great. The final thing you need to know is, well, what happens if you're given a rate and you're asked, well, how long did it take for the reaction to finish? Well, it's just as easy to do as it is to calculate rate. The finishing time for a reaction is just 1 divided by the relative rate. So if you were told that the relative rate of an experiment was 0.025 seconds to the minus 1, then the time taken for that reaction is just 1 divided by that number, which gives us 40 seconds. So the equations for rates are a lot simpler at higher. The only thing is that the numbers can get quite small. As soon as you're into the 1,000 seconds, you're at 0.0001, which can be quite difficult to deal with, but the equations themselves are quite straightforward. So hopefully that's helped you to understand the differences between average rate and relative rate, and the differences in the experiments that you would do and the measurements you would need to take.